Good afternoon to everybody all around the world. Thank you for joining the second webinar of the Education and Training on Image Quality Evaluation Tools and Corresponding Optimization, a working group of the European Union funded project i-Violin. My name is Graciano Paulo. I'm from Coimbra Health School from the Polytechnic University of Coimbra, and I have the privilege to be the leader of the work package 7. For this second webinar, we have two fantastic speakers that will give us an overview of the topics that I will show you in a minute, and I will also present our speakers in a minute. So this i-Violin project has several members. So University College of Dublin, the Otto van Gurik University, the University Medical Center Ljubljana, the University of Leuven, the University of Crete, the Klinika Dubrava from Croatia, and the STUK, which is a regulatory authority from Finland, and of course our my school, Coimbra Health School from the Polytechnic University of Coimbra, as I said. So this work package is about education training on image quality evaluation tools and corresponding optimization. And the objective of this work package is to develop an education training program for radiologists, radiographers, and medical physicists on how to implement optimization programs in CT procedures, including the use of image quality evaluation tools in view of reducing the exposure, especially on oncological patients, to ionizing radiation. This concept of this education training program is to be built through a multi-professional integrative approach, so involving radiologists, radiographers, and medical physicists as a strategy to stimulate teamwork and increase patient safety. I would like to highlight this word teamwork because I think it's the key of success of the future in medical imaging. This development of these education training program is based on the output that had already been achieved from other European projects, namely MEDRAFRET, Euclid, MEDIRAD, and Euramed Rock and Roll, and will include involvement of the European professional societies. So the outputs of the i-Violin project will be endorsed and receive inputs and comments from the European Society of Radiology, the European Federation of Radiographer Societies, and the European Federation of Organizations of Medical Physicists. In terms of specific aims, what we want at the end of this project is to develop knowledge, skills, and competences for the three professions or professionals involved in medical imaging, but especially in the optimization of CT procedures for oncology patients. Several projects around Europe and the literature is showing that there's a huge heterogeneity on how we do CTs, the output on the dose for the patient on those CTs, and obviously with a huge burden for the patients, obviously, but obviously also for the population in general, and obviously with costs for the system. Also, we would like to define a methodology on how to include image quality evaluation tools in daily practice as a strategy to reduce radiation dose to the patient from CT procedures. For decades, vendors have been using the concept of we have the best image quality, and because of that, we have been increasing the dose. But now it's a time that we need to talk about the best image for that particular clinical question. So we don't need the best image. What we need is the best image to give a response to the clinical question that we get to do that CT procedure. Also, what we want is to increase interprofessional teamwork in medical imaging department involving radiologists, radiographers, and medical physicists as a strategy to develop capacity in radiation protection. And also what we want is develop a European education training program that can be used as a model in all member states. And obviously to create synergies and collaboration within Europe and international organization as a strategy to disseminate and implement the education training program. So hopefully at the end of this project, we will be able to achieve these objectives. Now, these are the 4 webinars that will take place before we have 3 hands-on in 3 different hospitals to, let's say, pilot this methodology. Please use this QR code if you still haven't registered for webinar 3 and 4, which will take place in April on the 9th and 16th after this Easter break and Easter holiday. Now, as I said, for today, we have 2 fantastic speakers. We have Paula Tori from Stuk from Finland, and that I will present more in detail when she starts, and Christoph Hoschen. So Paula will talk about CT dosimetry and Christoph about image quality assessment. And these are the learning outcomes for this session. So basically, to understand the current CT dosimetry metrics, their advantages and limitations, I think this is very important, but will allow us to have a common understanding of what we understand about the different dose descriptors, to learn of optimal approaches to image quality assessment in CT, and to become familiar with future potential options in both automatic dosimetry and image quality evaluation. So by saying that, it's time for us to go to the essence of our webinar today with our speaker. As I said, the first speaker is Paula Tori. Paula is a medical physicist and radiation metrologist. For the moment, she's working at Stuk, which is the Finnish regulator authority, so the Radiation and Nuclear Safety Authority. And at Stuk, she's a principal advisor of the dosimetry laboratory and responsible for national standards in the field of ionizing radiation. Her main task is to make sure that radiation dose measurements made in Finland are comparable to measurements done anywhere else in the world, which is obviously a challenging task that Paula has on her hands. She's also an adjunct professor of Helsinki University and has a part-time job at Helsinki University Hospital as a clinical medical physicist. Paula, on behalf of i-Violin and on behalf of WP7, thank you so much for giving us your time and to spread this information to all around the world. I'm sure we have people attending from more than 100 countries. So thank you so much for that, and the floor is yours. Thank you.
Thank you. So I hope that now you can see my screen and hear me clearly.
Clearly now, yes. Can you repeat, because it was with some interference?
Okay, can you see the slide?
Perfect now. Now it's perfect. Thank you.
Yes, good. Okay, so my topic is CT dosimetry. First of all, I would like to thank the i-Violin consortium and Graziano Paolo, especially for inviting me to give this lecture. Graziano already mentioned the learning outcomes. I just would like to go through them for my talk specifically. So basically, we will go through the CT dosimetry metrics, and we will see what are the advantages and limitations of the current metrics which we are using, and also see what we would like to see, what dose quantities and parameters we would like to see in the future in the dose displays. So most of you would have this kind of dose report on your screen, and you have here this CTDI, VOL, and DLP. So my aim is to explain what they actually means and what is actually the patient dose. So the content of the presentation is the following. So first we go through why and when we need dosimetry. And then we go very deep in the topic, what is actually the patient dose. And then we look how the patient dose can be actually measured and calculated. So if it starts from the very general background, use of radiation in medical field, and just see where the radiology belongs in this field. So we have a lot of many radiation workers, and we want to protect them from radiation. So then we talk about radiation protection. And normally in this field, if we don't have any accidents or anything like that, we talk about dose rates which are in a range of micrograys per day. This means when we have this linear and no threshold model of impact of radiation as a function of radiation dose, we normally aim to go to as low as reasonably achievable. and we want to minimize the dose of our radiation workers. And because the conditions where we actually are exposed, we are not so easy to follow, and there are very big variation, we have to accept quite high uncertainties when we do dosimetry in the field of radiation protection. Then when we multiply this dose rate by 1000, we are in the field of radiology, we talk about milligrays per day. And in this case, we cannot accept zero dose in a way. So we need some dose to be able to do good X-ray images. But we also want to limit the dose so that it's not too high. So in this case, the range where we need to fix our dose is it's a little bit more narrow. So that's why we also need better accuracy when we do dosimetry. And then when there is a general rule when we want to do optimization, we are aiming to have uncertainty which is close to 10% or so. Then when we still go further, multiply our dose rate by 1000, we are in a level of grays per day. And this is what is happening in radiotherapy. So in the previous ones, we have less than 100 milligray, and then we are really dealing with stochastic effects. But when we talk about radiation therapy and we have high doses, we already have this deterministic effect. So the impact of radiation looks a little bit different as a function of dose. We want to have a very strictly defined dose to the cancer cells and avoid the irradiating normal tissue. So there we have even more strict requirements for the uncertainties. But today we focus on radiology. In radiology, we have all measurements. We actually have all those values which we have in displays, or what we have the requirements, or those diagnostic reference levels. When we want to estimate the dose, we always need some measurements. So all those displays are based on some measurements. And when we do measurements, we need some dosimeters. We need to do we need to use the dosimeters and do some measurements. And then when we want to compare the results to other doses, we really need to make sure that our measurements are accurate and comparable. And for this purpose, we need calibrated instruments. We need to use standardized and harmonized methods so that we have comparable results. And we also need to do uncertainty estimations. So when we want to compare two doses, it's very important to understand what is the uncertainty so that we can estimate if this comparison, if we have a difference between two values. So for example, in this dose display, if you have CTDI-vol is 9.24, and if you have a limit that it should be below 10, for example, if you don't know the uncertainty, it's quite difficult to say if it's really below 10 or not, if the uncertainty would be like 50%. We have another EU-funded project called TRAMEXI, where we actually focus on traceability in medical X-ray imaging dosimetry, because we have some challenges in the X-ray imaging dosimetry, and we are trying to solve them in that other project. There is also an IAEA project, because there is this kind of code of practice for dosimetry, and this is the TRS 457, but it's published in 2007. So there are quite many updates which are needed for this publication, and IAEA has this CRP coordinated research project to actually update this code of practice. If we then look a bit what are the doses and what are the number of exposures in the world at the moment, there was an UNSCARE report published in 2020. They publish these reports regularly, but based on this latest report, we actually had 4.2 billion medical radiological examinations per year. So in average, this means like every person is exposed once in 2 years. So this is really something which is covering something relevant for many people. Even, of course, this is not distributed evenly among us. So some of us are exposed more than once per year, and some of us might not be exposed so often. But I would say that I suppose most of us would would have at least one X-ray examination during our lifetime. So the topic is very relevant for all of us. So it's not only a small group of patients which are involved in this case. Of course, we have some patients like these oncological patients, which actually take a larger share of this dose distribution, and they might have several CT exposures within 1 year even. What is very important to recognize, there was actually some years ago, there was some discussion that if the number of CT examinations would go down because we have other imaging modalities like MRI, but this has not happened. So in comparison to the previous report of 2008, actually the number of CT examinations have increased 90%. So it's a huge increase. If you look at the collective effective dose, based on this report, it's 0.57 millisievert per caput, and the contribution of CT examinations is huge. So it was before 37%, and now it's 62%. So CT imaging really is an important topic, and we really need to make sure that we can optimize these radiation doses appropriately. So when we need dosimetry, we have different situations where we need to know the patient exposure and the dose. So first of all, we need to do, of course, based on the basic principles, we need to do justification. We need to estimate the risk of our exposure and compare it to the benefit what we have. So for that purpose, the radiologist needs the information about the radiation dose. This is really a tool for radiologists to make a decision. We might also have a concerned patient who wants to know if this is what kind of risk they have if they have this procedure. So this is one of the levels what we have on this table. The second one is the quality control. So we may have to make sure that our X-ray system is really operating correctly. And for this purpose, we also need dosimetry. We need to make sure that the technical performance of the system is acceptable. The third level is the optimization. We have technical protocols. We want to optimize them so that we have acceptable image quality, and the dose is on an acceptable level. The fourth level is really patient-specific dose estimate. So in some cases, we might want to do a specific estimation for an individual. And now we have all these different situations, and the quantities and the calculations what we might need might be a little bit different for these cases, and the accuracy requirement is definitely different for these different cases. And we will go through these cases, and in the end, I hope that we have the table filled with information. So what is actually patient dose? We have these measurable quantities, air, Kerman, and absorbed dose, but we also have a huge number of different quantities. And the challenge is that very often we talk about dose, or we talk about patient dose, without the specific definition what we actually mean. And this is quite challenging because there are really different doses available. So whenever we talk about dose or patient dose, we always should define what we actually mean. So here, different quantities have been divided in two. So basically, we have these measurable quantities, which are normally defined by ICRU and also guided by the IAEA. So these are these basic dosimetric quantities which can be measured, but they are not patient doses. These are normally something what we measure, and we actually want to use these harmonized, standardized protocols to do the measurements, and we can have very good accuracy for these technical measurements, but they are really not patient dose, but they are well-defined physical quantities. When we go to the risk-related quantities, they are defined by ICRP, and there are this local organ dose, and effective dose. Organ dose is, again, it's a total energy imparted in a tissue or an organ, and it's divided by the mass of the tissue and organ. So it's well defined. It's not a rough estimation. It's not changing when we have a new risk estimate. So it's really a well-defined physical quantity. There are also other risk-related quantities like effective dose, and there we have some averaging over gender and age or something, and they are not really well defined, and they might change when we have new information and data. But the risk-related quantities, they cannot be measured directly. They are patient specific in a way, and there is a large variation of conditions which should be considered when we estimate the risk-related quantities. And how we do this kind of considerations will define the accuracy of our estimation. So what dose we actually want? So if you look at the image, these are dose distributions. So if you see bright color, it's a high dose, and blue is lower dose. On the left side, we have the projection imaging, so normal radiograph. And there we normally measure the measurable quantities air kerma free in air, the star here. So we only estimate or calculate or measure the dose which is entering the patient. But you can see that actually the dose distribution inside the patient is varying quite a lot. So it's not representing patient dose at all. So it's just this kind of technical parameter. And if you want to estimate the patient dose, we need to do many steps before we can actually have the organ dose in our hands. In the CT, the situation is a little bit better because, as you can see, that the dose distribution inside the patient is a little bit nicer. It's not flat for sure, not uniform, but it's somehow more equally distributed when we have the X-ray tube is actually rotating around the patient. So there we have some variation in the Z and Y and X direction, but our dose quantities are actually estimating the dose in the, sorry, my animation is not working, but the stars should go around. So our dose quantities, the measurable quantities are actually estimating the dose in a larger volume. Okay, so when we have these measurable quantities and we go to the organ dose, this is our aim. What things are impacting on this conversion when we go from measurable quantity to organ dose? So first of all, the radiation conditions. What is our radiation quality, the spectra? What is the beam geometry? And then we have the patient properties, so the body size and organ location, etc. So first of all, in CT, we have a very nice situation that our measurable quantity is actually already taking a step toward patient dose. So we do the measurements inside a phantom, which is somehow simulating patients, which is not the case in radiography and 2D imaging. So we do these measurements in these phantoms. This is the head phantom, which is 16 centimeter, and the body phantom for 32 centimeter. And then when we do the measurements, we do measurements in different depths. So we do in the central part and in the periphery. And actually the concept of dosimetry in CT is defined in a way that we actually want to have a weighted average of dose in this kind of like a circle inside. So it's not one point, not in the center, not only one point in the periphery, but it's really like an average dose in somewhere in the middle. And this is really nice because then we can somehow, with this calculation, we average already the potential dose variations within the Y and X axis. Then when we do dosimetry in CT, we use typically this kind of 10 centimeter long pencil type ionization chamber. The quantity what it is measuring is the dose length product. Now I'm talking about dose, which is referring to absorbed dose in air. We actually often calibrate and use the term and the quantity kerma, air kerma, and kerma length product. But now I use throughout my presentation the dose term, and I mean the absorbed dose in air. In X-ray imaging range of energies, these are more or less the same quantity. So when we use this CT chamber, we actually do the measurements only for one axial sequential scan, but this is like measuring throughout the chamber from this, and then we have the beam is hitting the chamber in the middle, and we actually measure the whole profile. So we are integrating the whole dose, basically collecting all the dose, which is hitting the chamber. The basic definition is for infinity, but of course we cannot measure that. So that's why in practice, the measurement is for the range of the chamber. And this way we already start achieving some information in the Z direction, but now it's only one slice or one collimation or one rotation. So we don't have all the information yet. Anyway, now this is a very ideal situation. We have this kind of dose distribution, which we are measuring with this kind of chamber. So basically we have the length of the beam, which is now the collimation, the width of the tomographic section, and then the number of sections. And then we have some kind of tails here, which are now looks very nice. Not in real beam, it's not so nice, but we have these tails here. And when we measure with this chamber, we consider that they are actually moved on this side. And this way we come to this quantity, which is used in the name of this chamber. It's dose length product. So we are actually calculating the area under this rectangular. So it's the length multiplied by the dose. And this way we get actually the whole dose. And this is how the detector is actually operating. But the detector, what the dosimeter, this chamber, it doesn't actually know where the dose is coming. So it just collects everything from the chamber. And then this number, which is what it is showing, is directly proportional to the dose and length. And then from this value, what we get from this chamber, we can calculate what is the CT dose index. So it's calculated from this DLP measurement. And then this is a very important parameter, the CTDI. There is a challenge that some CT chambers actually show dose and use the unit milligray. And then this is just that they actually consider that the chamber length is this 10 centimeter, but it's not actually always 10 centimeter. It's just this kind of, there can be a little different effective length of the chamber. This might cause some additional uncertainties in the measurements. But when we have this kind of CT chamber, which is actually showing dose in milligrays, we always need to multiply the values with 10 centimeter to get the DLP. And then we can divide it with the collimation to achieve the CTDI. Okay, so now we have the data for one collimate or one rotation, but of course, when we have a real patient exposure, we do several rotations, and we need to estimate that one too, because in some cases, the table travel per rotation is not exactly the same as the nominal beam collimation. So we might have this kind of overlaps or gaps between the beams, and we want to take this into account. So that's why we need to divide the result, what we have, the weighted CTDI, which is measured in the phantom with the periphery and central part. We divide it with the pitch value, and then we get the CTDI vol. And this is really the average dose in the scanned volume. So it's averaging the dose in the X, Y, and Z direction. So it's not the point dose. It's not saying that dose is exactly this in one point, but it's really averaging everything together. And then if we want to estimate like the complete exposure of the patient, we can multiply this average CTDI, which is, it's not the point dose, but it's representing like one dose. And then we multiply it with the length of the whole exposure. And then we can always, again, have this DLP, which is actually representing the DLP of the whole examination. And these are the two values what we actually have normally on dose displays. So CTDI vol, which is like dose, and then we have DLP, which is the dose and the length product. And then we have here the information for which phantom this value is given. And this is quite important because it's, if we have a head phantom, the dose is double. So it's very important to also record what is the phantom for which the numbers are given. This is also one thing what we have developed in Finland. So we are actually not only measuring one rotation, but we put the phantom in the air, so it's hanging in the air, so that we can actually measure the whole protocol with with this one setup. So I think this is really nice way to do the CT dosimetry. There are some challenges related to new technologies. One of them is the wide beam. So our chamber is 10 centimeter long. And we actually want to also measure some the scatter inside the phantom. And now when we have these beams are getting wider, we want to have a big amount of information with one rotation. Then we have a challenge that our standard dosimetry system doesn't cover these situations anymore. So there are some guidance how to deal with this. There is the AAPM report. Then there was a few updates of IEC standards. And then I think one very nice publication is from the IAE Human Health Report, which is actually guiding, taking the information from these previous publications and guiding how to do dosimetry for wide beams. And it's also important to recognize that this is noted by the IEC standard, because this is also something what the companies and the manufacturers are following. So just very shortly, how we do this wide beam dosimetry measurements. We actually use the same chamber and same phantom system, so that not everybody has to buy a new system. So then first of all, we do measurements in the air, and then we just cover the whole profile, the large profile, with this kind of contiguous position of the CT chamber. This can be done for any collimation. And then then we do also measurements in this kind of reference width, which is now normally recommended is 20 millimeters. And then the measurements, the 20 millimeter reference collimation measurements are done also in the phantom. And the phantom measurements are then corrected based on the free air measurements. And here is my HUS colleagues with whom we were doing this kind of wide beam measurements, and we were positioning the chamber in the air. Other challenges what we have with new technologies are the new spectra. So first of all, this has been a big challenge with CTs, that we don't really know what is the spectra, what is the radiation quality, what we have. We don't really know very well the filtrations, what the companies are using. So it has been always a problem in dosimetry. But nowadays we also have this thin filtration, the extension of tube voltages which are used to the lower range. And the challenge is that this dosimetry equipment, what we are using for measurements, are calibrated in calibration laboratories with this kind of reference radiation qualities defined by the IEC. And CT, they are called RQT radiation qualities. And now we can do that, but then these calibration radiation qualities don't really cover the such clinical conditions. And we don't also know how these dosimetry equipment behave when we go outside of the normal typical range where we have tested them before. So this is something that we are also studying on this Tramexi project. Another challenge is that when we have new spectra, basically we cannot use the old conversion factors to organ dose what we have used before, and the factors are not readily available. One thing is also that we have nowadays these new CT systems where we have 2 X-ray tubes, and there we have similar challenges that can we do separate measurements of the tubes. Sometimes I understand it's not possible. And then if you have 2 tubes there at the same time, and they have different spectra, that might cause also additional challenges when we want to do accurate dosimetry. Another topic is the cone beam CT, where we, for example, if we don't have a full rotation of 360 degrees, then the whole concept of CT dosimetry doesn't work so well, because the idea of this averaging, weighted average, is based on this idea that we have a complete rotation around the patient. There are also, of course, the old topic, the dose modulation. This should be this should be tested that the dose modulation works correctly. This should be part of the quality control, and there we definitely need to use non-standard phantoms. But this is a full other story how to do it. But it's not really its place. But this definitely needs to be checked. Then we have covered partly the radiation conditions, because when we do these measurements in the phantom, they are partly covered. Of course, when we want to go to organ dose, we actually should take them into account specifically for that situation, because we take some radiation conditions into account when we do the measurements inside the phantom, and the beam is attenuated depending on the radiation quality. But when we want to estimate the organ doses, we actually should take into account what is the spectra what we are using. The other step is to take into account the patient properties, the body size and organ location. Let's look at this shortly. So when we look at the 2D imaging, so here we have a thorax PA for 3 different patient size. And if you look at the dose, what we would, for example, have on the breast side of the body, we can see that the dose for the larger patients would be completely different than for the smaller patients. So of course, the size of the patient will impact quite a lot on the doses. On the right side, you can actually see CT images of the phantoms, the body phantom, head phantom, a large patient and a small patient. And in this case, the CTDI wall would be exactly the same for all cases. However, you can clearly see that the dose is very different for these different cases. For that purpose, AAPM proposed a new quantity called size-specific dose estimate. This was proposed in 2011, and there they proposed to use this kind of effective diameter and correction for the CTDI to get this size-specific dose estimate. Then there was some further development. They were also introducing this water equivalent diameter, because of course, if we compare just the diameter of the patient on the chest position and the stomach or abdomen position, this will have little bit very different attenuation properties. So they decide that it's much better to have this kind of water equivalent diameter. And in 2019, this was also implemented in the IEC standard, which is very good, because then the manufacturers can also implement the SSDEs in the dose displays. And I think many new systems, CT systems, already have the SSDE dose display available. And there was one important change in this history. So AAPM report was actually proposing this SSDE, the calculation from the central part of the scan volume, but then in the IEC standard, they actually propose this average dose across the whole scanning volume, which is also representing much better the actual patient dose, because there can be some big variations in the size of the patient within the jet in the jet direction. One publication what I also want to warmly recommend is this AAPM report 246, which was published in 2019. It's about organ dose estimation, and it really collects all the information of the previous publications and gives really like a full package of organ dose estimation. So I really like this publication too. So what are the challenges related to organ dose? So we have this phantom, we have the peripheral central measurements, and we are estimating the dose in a specific part of the phantom. But when we put the patient there, we can see that maybe this circle is not really representing the dose, organ doses or all organ doses. And then the question is that, okay, we know the dose more or less in average in this part of the body, but when we go in deeper organs, maybe the dose will be different. So the organ location, another challenge is the partial irradiation. So if you have an organ which has 50% of the organ gets 2 grays and 50% of the organ gets 0 grays, the organ dose will be 1 gray. So sometimes it might be important to know what is the maximum dose inside the organ, but the organ dose definition is for the average. So it doesn't tell us the maximum dose inside the organ. So it's not the dose volume histogram what we have in radiotherapy, for example. Another point is that when we look at how the organ doses are changing when we have exposure from different directions. So when we start from left, the organ dose is increasing the stomach. When we go to the back, the organ dose is increasing more for the kidneys. And on the right side, we have more dose to liver. So especially when we have partial, we don't have full rotation, or we have this kind of helical system. So this will definitely impact on the organ doses, so that the dose distribution is not flat, and depending on the organ location, also this will impact on the organ dose. So how to do the organ dose estimation? We can, of course, use published values. We can go to publications, say typical organ doses are those. We can use the measurable quantity with some limitations. We can use the measurable quantity together with generic conversion, or we can use the measurable quantity with patient-specific conversion. So let's go through them quickly. So if you just take the general value from a table or publication, it means, of course, the uncertainty can be very high. But in actually many cases, this is enough. We don't need to do measurements. We can just estimate, okay, in a computer, in CT, chest CT, we have a typical dose of, let's say here we have 6 millisieverts. And the radiologists need to make a decision if they will propose to have a chest X-ray, a normal X-ray, or a CT, or an MRI. So probably this level of accuracy is enough for many cases what we have in a clinical practice. And of course, when we have a patient, concerned patient, this might be also enough that we just say that dose is low enough and risk is low or very low. So we don't need to, if a patient calls to me and says that, okay, I had this CT, should I be worried? I would not go to patient-specific dosimetry in this case. Then if you just use the measured quantity alone, so we have the data here directly available, the measurement can be accurate, but it's not the patient dose. The CT-di-Vol really represents the dose of a completely irradiated central organ for a large patient. And the CT-di-Vol it's a very useful technical parameter, and it can be used for diagnostic reference levels, for example. But when we have the variation in patient size, there can be large uncertainty. So that's why I really like the concept of size-specific dose estimations. So it's a huge step forward. So it can already give us some kind of indication of an average organ dose. Then if we have the measured quantity and we do a general conversion, so it means that we can use, again, a value for a publication. What is the conversion factor from CTDI to something, to an organ dose? We can do phantom measurements, and then we can do simulation with some generic models. Of course, the uncertainty of these methods really depend on the model what we are using. So if you only have this kind of phantom, and we want to estimate the dose for a patient which is not exactly this shape, might have a larger patient or smaller patient, of course we make bigger errors. Or if our patient model is not representing the actual patient. Of course, these ICRP, ICRU reference phantoms are quite good if you want to estimate, for example, effective dose, not individual dose, but some kind of generic average. Then they are basically the only choice. We should not do individual estimation if you want to do this kind of calculation, generic calculation, for example, for the effective dose. So with this system that we have measured quantity and general conversion, we can actually cover most of the scenarios where we need dosimetry. For example, if we want to do optimization, if we want to just optimize dose, we don't even need to go to organ. Organ dose. We can just estimate the dose level with the CTDI alone. But if we want to, for example, start adjusting the tube voltage or change the spectra, then we need to take this into account when we calculate the organ doses, because otherwise we are just comparing the measurable quantity. So, but if you want to do it properly, we should take this into account. If we want to, for example, do optimization for different patient size, of course, then also our patient model should be for that patient, for that range of patient sizes. Otherwise, the optimization is not so accurate. Then for this purpose, we have several tools. So we can do the measurements with different kind of dosimeters inside a phantom, or we have all these kind of programs available where we have different patient models. We have different selections of scanners, and beam parameters can be selected, And of course, then they have different accuracies depending on the program and the number of conditions what we can take into account when we do the calculation. In the Medirad project, Greece and John Damilakis developed the CityRad program, which is now further developed under the i-Violin project. So there you can do calculation for the adult and pediatric model. You can actually put the CT image to estimate the water equivalent diameter. You can do calculations for a few scanners, for few indications, few tube voltages, and take into account the modulation in some range. And then it gives you dose to some organ doses and even some risk estimations. So this is freely available, and this is one of the tools available. The last but not least is the level where we actually want to do patient-specific dosimetry. So to be able to do it really individually for an individual, we should actually have a full description of radiation conditions. We should have actual patient images, which we can use for Monte Carlo simulation. And in this case, we can actually achieve an uncertainty which is lower than 10%. But we need to take a special care of these conditions. The one challenge is that how to estimate the organ doses for those organs which are not within the imaging range. So then even there, we would probably need to use some kind of model to estimate the dose, which is for the organs which are not in the primary beam. I think I was trying to think what are the potential scenarios where we really need this kind of accuracy for. Do we need an individual dose estimate? And I just came with the one example, like pregnant woman was exposed. She had a miscarriage. There is a legal process ongoing. So there might be a need to do individual dose estimate for this patient. Maybe there are many others. And I was also thinking maybe if you have some potential scenarios for this purpose, you could put them in the chat. So I'm almost finalizing my presentation. So first of all, a summary about the accuracy of the patient dose. If it just take the dose from the published table, it can be enough for some situations. Uncertainties are high, but we are not taking into account the specific dose, not the radiation conditions, and not the patient properties. When we use the measurable quantity, the measured quantity can be maybe measured accurately, but it's not the patient dose. And when we want to convert it to patient dose, organ doses, there will be probably some additional uncertainty components depending on the situation where the actual patient is irradiated. This measurable quantity is useful for quality control, and this size-specific dose estimate is very useful development in this field. When we do measurements and general conversion, uncertainty is very dependent on the method used, and it's still not patient-specific if we don't do it if you don't take into account the patient-specific beam properties and the patient properties, and then we can have a large uncertainties. But we can do it if we can do it well, and we can take into account the patient properties and beam properties. The uncertainty can be also very low. And only in the case when we really do patient-specific dose estimate and take into account all the patient properties and beam properties, we can really achieve very good accuracy for that specific patient. But in many cases, it might not be practical, so we would probably not do it for every patient every time, but definitely for research, it's very important. So that the table, what we had in the beginning, now we have some kind of idea what is the quantity. So in justification, we need a typical dose. It might be an effective dose in some case, an oral dose. For quality control, we need these measurable quantities. Optimization, we might be able to use just a generic organ dose, but when we want to do a patient-specific dosimetry, we need the organ dose for that individual. And then the accuracies, of course, depending on the method, how we do this estimation. So just a few words about the future. So if you do this manual, this organ dose estimation, it takes some time, but actually the most of this information is already available in the X-ray systems, in the DICOM headers and those structured reports. So basically, we could already get this data automatically from the X-ray system. So I really think that there is a need for collaborative work and work from the manufacturer side, and I'm sure they're working hard on this. And we already have some tools available which provide us the organ doses. And however, we should keep in mind that there's always some measurements behind that value, whatever display we have. And it's really, we should make sure that we don't not just put the patient in a black box and don't know what is happening there. So we should make sure that even if it gives us some kind of dose estimation, we need to make sure that we can rely on the value and it's verified. And normally this is the role of a medical physicist is responsible to making sure that the doses and dose displays are correct, giving correct values. However, whatever data we have, usually we need to do some generalizations of conditions and patient properties, and this always impacts and increases the uncertainty. So now we know what the CTDI-Vol 10 milligram means. It's basically, in some cases, it's an appropriate estimation of organ doses in the average. However, the beam and patient properties impact a lot. And in the future, we hope to have accurate dose data easily and automatically available. And we will have this webinar 3 and 4 where we have more information about dose management and dose reduction tools. This is the last slide, take-home message. Think what accuracy level is required for your dosimetry purposes. Select the method based on that. Remember that the measurable quantity is the starting point. Use calibrated equipment and harmonized procedures. The size-specific dose estimate can be used as a rough indicator of average organ dose. Check your dose displays and automatic calculations. And when you convert organ dose, make sure that you take into account the radius conditions and patient properties and estimate the uncertainties. Thank you.
Thank you, Paula. What an outstanding presentation. Very, very comprehensive overview. Thank you so much. I will kindly ask you if you are available to keep with us till the end of this webinar for the question and answers. We have already some questions from the audience, and yes. I'm sure that it will be very interesting. Thank you. Can you please stop sharing your screen? While you stop sharing, I would like to ask all the participants to please put the questions that you have for our speakers in the chat box, and then at the end they will be or in the Q&A, and at the end, the chat box, or in the Q&A, preferably in the Q&A, and at the end we will come to all these questions. We will move to our next speaker, Christoph Huschen. Christoph, thank you so much for joining. Already late in Germany, also was in Finland, 2 hours, even more, I think. I don't know if it's 2 hours, 1 hour in Finland. So Christoph is a professor of medical systems engineering at the Otto van Gulik University. I hope I pronounced it well. He's focused on new medical imaging or diagnostic approaches, namely AI and image quality assessment, as well as medical radiation protection. His PhD is in the natural sciences at Magdeburg, but already in the field of medical image quality assessment. He's very much involved in several European projects like Madeira, Euramed Rock and Roll. Also, he's involved in i-Violin, Imprint, and he is a SPE fellow. And is also a spokesperson of what is called the umbrella of the radiation protection in Europe, which is the MENIS consortium, and member of the German Radiation Protection Board. And he had several functions in the Euramed platform. And I had also the privilege of working with Christoph in the last, I don't know, I lost it. many years. Thank you, Christoph, the floor is yours.
Thank you very much, Graziano. Thank you very much for this kind introduction. Thanks everybody to stay here with us for the second talk of this webinar. Let's get started immediately so that you have time for questions in the aftermath of that. So as an introduction, if we look for what we just heard by Paula, then you have learned that radiation dose in CT imaging is really very important, as CT imaging can be or is really very much needed. So it has a great benefit to patients in the most cases, but it can also be harmful due to the presence of ionizing radiation. So therefore, we should limit radiation in a way to the minimum required amount for a dedicated task, and that is what Graziano also mentioned in advance. But on the other hand, if we reduce the dose too much, then it can lead to a reduction in image quality, and that might be even important or detrimental for the image diagnosis, or for the diagnosis based on the imaging. So therefore, we have to always have to make a trade-off between dose reduction and image quality. But if we want to do that, then we need to know what is image quality. So if we want to optimize medical imaging procedures that are based on the application of ionizing radiation, then it is of major importance to allow the best possible benefit-risk ratio. And actually, we are currently discussing whether it is benefit-risk ratio or risk-risk or benefit-benefit ratio for each individual patient. And I want to highlight that it is really important to do that for each individual patient in any medical imaging situation, but especially also in oncological imaging. As Paula also mentioned, there are people that will have more imaging procedures than typically for a standard evaluation outside the oncological world. We also need a reproducibility in achieving both image quality and patient exposure that are consistently appropriate and patient and indication based in clinical practice. And with reproducibility, we mean that this is really should be the same everywhere where you really do such imaging for the purpose of diagnosing or staging or whatsoever. So this is really the essence of optimization of an individual imaging procedure. And if we see that, then we can say that we need some kind of an objective image quality assessment in patient images. At least we need to describe our systems first of all, and then the best possible way would be to have an image quality assessment for the images that we are using for diagnosis. If we want to do that, then we need to define specific criteria for which image quality is appropriate. So for the appropriateness of image quality for each clinical indication, and that would ideally result in a technologically independent ground truth for confident and reliable diagnosis. What do I mean with that? Well, it should not matter whether you have a CT from vendor A or vendor B, or whether you have a 10-year-old CT or a 2-year-old CT. With all the technical new developments, whether you say what you need for a clinical indication. So the image quality that is appropriate for your diagnosis should not depend which system you are using. It should just maybe not allow this for certain scanners, let's take it that way. Then you should use another scanner if it is possible. So there is currently no clear definition what elements of image quality are appropriate for which clinical task. And therefore, we need to target our research on image quality on a single patient encounter basis as an essential component of radiation protection and optimization of medical imaging. But now, as we have talked about such quite a while about what are the conditions, what do we want to describe with image quality, let us see how we can describe image quality and what can we do about that. So first of all, we have to divide image quality assessment in two major divisions, let's take it that way. One is the so-called subjective image quality assessment, and the other hand is the objective image quality assessment. The subjective image quality assessment there we assess the quality of images using radiologists that do evaluations of images under clearly defined conditions. For example, you can use a so-called visual grading analysis, for example, the ViewDex system. And in most of the cases, you need to know the ground truths for classification tasks, which you could also do for machine learning. The problem here is if you want to have radiologists, and actually you typically need, depending on the number of images and the questions that you have for image quality assessment, you need like, let's say 5 to 7 radiologists. And you need to have them reading like hundreds of images for some comparison. So you see, this is really very time consuming. And still you do have a large inter and intra-observer variability. So that makes results uncertain. You have heard a lot of uncertainties with the talk of Paula. And here we again have quite a bit of uncertainty and the results unclear. So that is the subjective image quality. But I also want to make one point that I think is very positive about subjective image quality, because this really reflects the clinical case. So that is where you are when you look for the radiologist reading the images. This is also, he's reading that subjectively himself. And also if we determine ground truths for machine learning programs for computer-aided diagnosis, there's still the readout by the radiologist that gives us the ground truths, right? So this is reflecting the clinical case. On the other hand, we have objective image quality assessment. There, the quality of the image is measured by the quantitative matrix. Ideally, you would not have a manual user interaction that is required. This could be then applicable to huge data sets occurring during daily clinical routine, and it could enable deeper insights into relation between different imaging parameters and their effect on image quality. So if you read that, that really sounds great, right? The problem is, so far, in objective image quality assessment, and we will talk about that in a minute, we typically use just specific phantoms or specific tasks that we provide to the imaging system, and we do not look into the single image of a patient. Why? Because it's much more complicated to find possibilities to look for the quantitative matrix that we want to see. Now let's look for the matrix. What is really determine image quality? So what are the influencing factors in determine image quality? Well, there are 3 main components that we should look at. So first of all, and you will see that that will be most relevant, so therefore it is put here on the first left-hand side, is the noise. What we typically see first is the contrast. So that is why it is in the middle. And then we have the sharpness, which is also very important. As you can imagine, if your image is not sharp enough, you might overlook some certain things. So what are influencing factors? And here I took for simplicity the influencing factors for the projectional images that are the basis of the CT images as well. So noise is determined, first of all, by the system noise, which is depending on the diodes, on the electronics. But it also, and even to, in most cases nowadays, to a stronger part, to the dose. This is the quantum noise that is influencing that, and we will have a look at that as well. And actually, this is the one that is directly related to the dose reduction potential. So if we reduce the dose, then the noise will increase. That's the drawback. Noise and contrast will be influenced by the object density and as well, and that's a pity for people like me, by the object thickness, because we will have scatter effects and we will have also additional noise components. And then the contrast is not only affected by object density and object thickness, but also by the radiation quality. And you heard what Paula told you already about the radiation quality and the effect on dose, but it will also affect the contrast and partially even the sharpness. And then the contrast as well as the sharpness is influenced by the dynamics of the detector, so by the potential of the detector to reflect the contrast. The sharpness is in principle reflecting what we call as physicists the spatial resolution. This might be the spatial resolution of the detector, but it is also influenced by the geometry of your imaging system in general. The contrast refers to the difference, in intensity in the region of the image corresponding to different uptakes for nuclear medical imaging or to different absorption for CT imaging. And here you see what we mean by that. So this is the background, so to say. And here you have a region of interest where you have a stronger absorption or a stronger uptake, or, well, this is less uptake. This would be a stronger uptake in nuclear medicine. And then you can define your contrast as the signal in the area of interest, the region of interest, minus the signal in the background, divided by the signal. Now, one big problem already occurs here, because this is not the only definition of the contrast. Actually, there are two major definitions of contrast. So one is the so-called Weber definition of the contrast. This is the intensity in the region of interest minus the intensity in the background divided by the intensity of the background. So you see, this is what I mentioned in the slide before. On the other hand, we have also a definition of contrast by Michelson. And here it says this is the intensity max minus intensity min. So you could also say intensity in the region of interest minus the intensity in the background divided by the sum of both. So you immediately see this is something different. And when you talk about contrast, you should be aware about what kind of contrast you are really talking. And just to show you an image by the time now, this is an image that I just took from Wikipedia showing the visible contrast. So you see on your right-hand side that the image looks much better. It has a higher contrast that we can visualize. So therefore you can also see much better, for example, the clouds in the sky, and also the details in the water or in the trees. So obviously it's important how our system is able to transfer the different signals into a signal that is visible for us, so into an image. And this needs to be characterized. Now let's come to the point why I said noise is really important. And this is directly related to the appropriateness of an image. So what you see here is, again, an image, but not an image from the medical field, but from the field of photography, actually. And that was in a book by Albert Rose from 1973. So it's more than 50 years old, and his book was called Vision. And he wanted to describe the effect of dose and the, well, exposure in his case, and the relation to the number of photons. And what you see in your lower right case is a photograph as it was taken originally with 28 million photons. And then he did a way to reduce the number of photons step by step by around a factor of 8. It's not always exactly a factor of 8, but around that. And you see some noise appears and it gets worse and worse and worse and worse. And obviously, therefore, it gets much more complicated to detect the situation. So assume this is the reality, this is a ground truth, And we really need to diagnose this ground truth, as the radiologist would need to do. Well, if we would need to use this number of photons, that would mean a really, really high dose. Actually, radiologists are working on signal-to-noise ratios in this range here. And they diagnose the one on the right-hand side by that. So they have the image bottom left, and they have to do the diagnosis bottom right. That's what our radiologists are trained to. Quite fantastic. If I tell you the nuclear medicine guys, they use an image with that kind of signal-to-noise ratio, which is the middle of the upper row. And so they live with much more noise, but well, they also have some advantage, right? They only look for the function, so they don't need to really see every detail of that. They just need to see where it is shining up. Nevertheless, you see that there are quite some interesting challenges if you talk about the noise in an image and the relation to image quality. I'm referring to that with that much detail because you really see that the question, which image quality is appropriate for diagnosis, will depend on the single case. So what are the noise components? If you look for a total image, then we will have some relevant image content, hopefully. Typically, if we have a non-diseased case, then this is just the anatomical background. In case that there is a disease, it's the anatomical background plus the structure that is referring to that. Then we have the so-called anatomical noise, and that's noise due to the patient that cannot be separated from each other. The next part is the quantum noise, and we already talked about that. That comes out of the way how we produce the image, how much dose we give, how much photons we allow the system to detect. And then we have other system noise, which is, for example, the detector noise, and that is typically has a part that is correlated and an uncorrelated part. And we call all these last three ones, the quantum noise plus the other system noise, the correlated and uncorrelated one, the so-called system noise. So for the quantum noise, the X-ray photons that are generated by an X-ray tube are spatially varying according to the Poisson distribution. The detector transfers this noise depending on spatial frequency and adds noise components. And therefore, we typically measure the so-called noise power spectrum, which is also called the Wiener spectrum. This describes for each spatial frequency which power of the noise is localized in a small frequency interval around the given frequency. Now we come to the spatial resolution. The general definition is based on the so-called Rayleigh criteria. So that is how can I separate two neighbored objects? And here you see in the upper row, these two objects can be very well be separated. And if you see the profiles, you see that they are distinct. If you look for the middle row, it is much harder to separate that. It could be two objects or one object with a strange form. So you see that there the profile already also looks a little different. There is still a dip, which might indicate that there are two objects, but it is not completely separate, right? The two profiles are not completely separate. In the last case, in the bottom row, if you just draw the profile through this line here, then you would see that there's basically no dip even anymore. And so in the profile, it's basically no longer distinguishable whether you have one object or two. So if you see that, that is what we want to describe. But what is a good quantitative description of this spatial resolution? Well, people are working typically with a so-called modulation transfer function, or MTF. This modulation transfer function, I know this is a little bit mathematic, but I hope that you will forgive me on that. If you have a CT image with just one single small dot, and this single small dot would be ideally imaged, then this would be the so-called point spread function, which is just the cuts through this one point. And if the point is really distributed ideally on a very single point, then you do not have a spreading of that. And that would mean that in this single point that is imaged here, you would see all frequencies in the same way. And therefore, this is called the modulation transfer function, which would be, in this case, just one constantly. So all frequencies are modulated by the detection system in an ideal way, are giving you the original point as an input signal. This is on never the case, because you have a detection system that will lose some sharpness because of the pixels, because of the detector elements and so on, or the detector matrix and so on and so forth. So we do get a real point spread function. So that's broadened compared to what you see here in the upper row. And therefore, we do not have all frequencies embedded in the same way as before, but now we have a reduction of the higher frequency components, and the modulation is being reduced for each single frequency. Having a noise power spectrum, having an MTF, we can determine the so-called detective quantum efficiency, which is related directly to the so-called noise equivalent quantity. So radiological image quality set by a physicist depends on the distribution of photons in the detector plane and on the signal-to-noise ratio for each detailed size. So we have to really do that for each detailed size. This is described by the noise equivalent quanta on each single frequency. The DQE then, and you will often see that as, for example, describing detectors of a CT system, is given as the ratio between the noise equivalent quanta and the impinging dose. You heard about dose determination before by Paula, which described the ability of the detector to produce a signal-to-noise ratio as good as possible for a given entrance dose, depending on the detailed size. So the DQE is nothing else than the signal-to-noise ratio squared at the output of your system divided by the signal-to-noise ratio squared by the input. To summarize, NEQ describes the image quality, so that what we would be looking for today, and DQE, the detector quality. If we have that, we can try to describe diagnostic performance. So first of all, we generate an image, and therefore we generate a noise equivalent quanta. This is depending on various parameters, and I will come to that in a second. Then we have to detect what has been done here. So this signal-to-noise ratio has to be detected first by the detector. So this is a detection task. And then by the software, which can be summarized as a presentation. Here we have our image. The problem is this is the clinical performance. And actually, we don't know what the human observers do with the image. If we would know that, we would be much more happy. So here are the parameters. So you see this is KVMAS, signal imager distance, signal object source object distance, focal spot size, and so on. You have these parameters for the image processing. And then, and we should not forget about that, a lot about the human observer, like adaptation, the age of this person, the experience regarding the clinical questions, the knowledge about the patient, and so on and so forth. Now, what I showed you first, because it's so easy, is to transfer everything into the frequency space and to look for how sinusoidal waves are transferred. So that is the so-called Fourier-based approach. However, this Fourier-based approach assume, among others, some aspects that are not trivial. Actually, one assumption is that the image result is spatially invariant. This is true for analog systems more or less, not completely, but more or less. For digital medical systems of today, it's not realistic. So therefore, there's another approach, the so-called task-based approach. This tries to model the system behavior by matrix operators. It's difficult and time-consuming and not that intuitive, but it has some other advantages. So what do we do here? Well, we try to describe how an object F is transferred into an image. And we say this is done by a transformation matrix, which describes the system. And so we just need to calculate this H matrix. For the noise, we would need to determine the covariance matrix, which just says something about how strong is the interrelation between neighboring pixels. Both of these types are used in pixel-based signal-to-noise ratios. Here's some more mathematics, and I swear it won't be too much more after this. So this is our image, this is our object, and this is the H matrix. This is of size m by n, where m is the number of pixels in the image, n is the number of elements in discretized objects. And then you can do a singular value decomposition with orthonormal basis vectors of H and a diagonal matrix. This consists of the singular values of H. The theory of linear systems then would show you, and this is a book of 1,500 pages that shows that to you by Barrett and Myers, that the MTF is basically the eigenvalues with respect to the orthonormal systems when you use this orthonormal system. If you now have a linear shift invariant system, then these eigenvalues are equal to the singular values of H, and by that you can determine the MTF. For the noise, we have on the one hand side the noise image. We separate that into regions of interest. In the Fourier-based approach, we calculated this NPS, which is the Fourier transformation of the ROIs and average, then this constitute the NPS. In the task-based approach, we calculate the covariance matrix, which means just the correspondence between the different parts here, which you see as a calculation here. There are pros and cons about that. Here is one pro. If you look at that, and this is just a CT image where we did a noise analysis for different filters of the reconstruction. And you see, we can now, in this new method, in the task-based method, see the symmetry, the radial symmetry, as well as the structure of the noise very well, which we could not do in that same way with the noise power spectrum. So there are advantages and disadvantages of the task-based approaches. The advantage is you can perform it directly on digital images. So you can just look for what kind of task I want to use, and then you put it in and you do your evaluation. You do not have a problem with the constraints for Fourier mathematics, and the structure of the noise is visible, as I just showed you. The disadvantage is there's no correlation to spatial frequency. There's quite high workload for measurements and a high computational load. And therefore, it's difficult to generalize results. So now we have seen task-based method and Fourier-based method. And here you see the difference in the signal, how this is calculated in the different approaches. This is this H matrix on the difference in the image, in the object. And this is the Fourier transform of the difference in the object. And here you see how the signal-to-noise ratio is calculated, and I won't go into detail for that. So what are the challenges if we look for this objective image quality assessment? Most existing image quality analysis approaches are based on dedicated phantoms, as you see them here on the left and in the middle. And from that, you try to determine some certain parameters. But this is a CT image of a human thorax, and it's not quite similar, right? So the challenge is Either we can do subjective image quality assessment, or we develop a method to analyze the quality of patient CT images directly. For observer performance studies, so subjective image quality assessment, there are two techniques that are possible. I don't know what's happening here. Sorry for that. The contrast detail study or receiver operating characteristics. In the contrast detail study, if the system will let me do, you have a reference phantom with different contrast and lesion sizes. And in the ROC study, you have phantoms with simulated lesions or clinical images. Now we can use that. The question is there a lesion? If yes, this is weird. And we really have a lesion, then we talk about the true positive case, the sensitivity of the system. If we say no, but there was a lesion, then it's a false negative. And on the other hand, if we have a yes answer, if there is no lesion, then it's a false positive. And if we have a no, then it's a true negative, which is a specificity. And now we try to calculate true positive fraction, false positive fraction, and we do get these images here, which shows us this is a contrast detail diagram analysis, and this is the ROC study, where we plot sensitivity over 1 minus specificity. So there we can do these evaluations. The problem is we do need a lot of effort, as I told you before. So because of that, people thought about using or looking for the decision, and typically we have a binary decision. This is exemplified by the task of detecting a signal or abnormality. A detection task is a binary decision because there are two true states, the normal state at the absence of a signal and the presence of an abnormality or a signal. H0 is, by the way, often called a negative or disease-free finding. And often it is impractical to determine task performance of imaging studies from studies involving human observers because reader time is scarce and expensive, and especially for a trained reader such as a radiologist. To address this issue, there had been mathematical model observers being developed, either to predict human observer performance or to estimate ideal observer performance. The observer models described assume that images contain exactly known additive signals. For an ideal observer, and that's the only one that I want to refer to here in this talk for time limitations, this computes the likelihood ratio or its logarithm. It's optimal according to numerous criteria. It is linear for Gaussian data, usually nonlinear when data are non-Gaussian or there are other sources of variability like random objects or random backgrounds, and it can be pretty difficult to compute. In general, you should use the ideal observer if possible. It captures all information in the data and adds no noise or uncertainty. But it is often not calculable. So therefore, people are using, for example, the Hotelling ideal linear observer as the next best thing, or an optimal linear discriminant after processing data through channels, the so-called channelized Hotelling observer. These are useful predictors of human performance, but it is still not a completely overarching task because it's not referring in all cases to real clinical images. So therefore, I want to end the session today, or my talk today, by looking with you forward using IQA in patient images. It seems to be the most promising approach to me, and that was also what was done in i-Violin so far, for daily practice optimization of image quality. So we do not no longer look into the systems, we really look into patient images. Therefore, we need to have radiologists define the structures necessary to be visualized for accurate diagnosis for a given task, and then try to determine objective image quality related parameters on real patient images or even on such structures in the real patient images. The parameters that we use for the objective quality assessment in patient images are estimated features like the modulation transfer function, the noise power spectrum, the power spectrum, and we also introduced a new metric as a power spectrum divided by the MTF. And here you see an example from the i-Violin project from an abdominal CT image. where we mark a region. The red region is the psoas muscle, which can be used here as to determine the MTF. And then the green region is a region outside the psoas muscle where we can determine the noise power spectrum, because there are no separated structures. And here you see then how the gradients on each position are determined, and then the structures or all these lines are superimposed, and from that we can determine the line profile, and from that we can determine the MTF. So the summary of the methodology is we have an algorithm framework for the CT-IQA using features such as MTF, NPS, and power spectrum. We select ROIs, we compute features, and then do a classification in some cases. I will come back to that in a minute. And then we would have a result, whether an image should have an acceptable image quality or not. So we have an automatic edge detection, an estimation of the gradient direction, and the MTF computation. We identify, or we need an identification of a homogeneous ROI for NPS estimation. And then we define various features with which we can try to classify images. The classification would be done using the support vector machine. And here's a program. This is how it looks like. You can find it in the internet. Already it's CT-IQA at the OFGU website. And you put in some data. We are trying to optimize it so that it can still be more automated. And also we will have to overcome one problem, because so far the classification is only on chest CT. So what we can do is determine the parameters, but it will not classify for other imaging types so far. So you put in a single DICOM image so far, so you have to look for the positions that you need. So the XY value here, for example, for the major fissure of the left lung, and the position for the ROI for the noise power spectrum. And so this number 1 contains the structure, and number 2 the homogeneous area. And then you put in the ROI size. Typically you would use something like 18 pixels or something like that, and then it will calculate the parameters. Here are some correlated results. You see that for the chest now. So this is 2 examples for a chest CT. The one on the left-hand side rated as acceptable, and the one on the left-hand side as non-acceptable. And here you see the corresponding MTFs. So the area under the curve of this MTF is higher for the acceptable one than for the other one. And here you would see the calculation of the noise, which has a number of steps that we need to do. So we have the CT image, we select a ROI, we have a detrending, and then calculate the NPS. And that's what we do get. And you really have to be sure that there's no structure in that area. Because of that, and because we saw that even though in many cases we could get a good separation, not in all, we looked for the differences between structures in good images and bad image qualities, where the noise power in total and the MTF were nevertheless quite similar. And here you see such an example, and here you see that the noise is overlaying to the structure, and therefore we were in the bad image, and therefore we were looking for this value of power spectrum, which is done in the same area as the MTF and the MTF, to get an additional value. And you see that the shape of the curves is completely different. So if you put that, then you can see that there are different parameters that allow a separation in certain ways between the different parameters. And if you put them all together, you get quite a good classification. And we want to do that for other areas as well. That's what we are working on. So we do have a software tool to determine image quality parameters already in patient CT images. It works basically completely for chest CT. For abdominal CT, you can also determine the parameters, but the classification is only working on chest CT. And also there we want to do more automatization. So the i-Violin project in principle is too small to conduct large reader studies. So we cannot classify them, but you could help us. If you want to send us images from your institutions, please anonymized, which you already classify as acceptable or non-acceptable, we can make use of that for our calculation. We do not have a complete automatic detection of suitable structures yet, but we will work on that after the i-Violin project, hopefully. And having said that, I'd like to thank you very much for your question, for your attention, and I'm happy to take any questions.
Thank you, Christoph, for this outstanding overview of everything that relates with image characteristics. It was really helpful. I will kindly ask you to stop sharing your screen and invite Paula. We have several questions. The audience is typing down questions, and we will start the Q&A part now. And I will, to make this more interactive, I will both of you please reply. So we will not focus the questions to Paula or to you, Christoph. Please feel free to jump in whenever you like. So
I actually,
yeah,
Graciano, I actually tried to reply directly in the chat, and so I have some replies prepared, but it didn't work, so I was not able to send the.
Okay.
So
okay.
I'm happy to answer.
Okay, no problem. Great. We were honestly speaking, both your presentations were so fantastic that we could spend the rest of the evening here discussing about what you presented. But let's start from the beginning, and especially because both of you spoke about several times the same word, which, to be honest, for those people in clinical environment is completely challenging, which is the word uncertainty.
Mm-hmm.
So basically, what you have presented to us is a world of uncertainties. So the point is, and because Paula, you showed us several ways or the reasons why we need those descriptors, and the main one, honestly, my interest is about the DRLs. So the first point is, how can we establish these DRLs when the uncertainties are so big? This is the first point. The second point is that, and because you are also involved in radiation metrologist, how can we rely on the dose descriptors that come from the equipment when in the vast majority of them, there are no medical physicists involved in these departments? So is the output that we get from the equipment reliable or not under this world of uncertainties?
So first of all, the uncertainty is an important part of the measurement, but of course we can, in some cases, we can accept higher uncertainties. So I think DRLs is a good example. So we are not aiming to estimate the dose for an individual, but we are really using it as a tool for optimization. So we are calculating average over a large range of different size of the patients. So then I think DRLs, for example, these displayed those quantities and the measurable quantities are good quantities. And then the uncertainty, it's always, depends on what accuracy we need. But I'm happy to say that, definitely there is a huge development in this field. So I see that it's going more and more to that direction, that we are taking into account the patient properties and the beam properties, and the companies are working. So there was a question about AI. So definitely this is one big challenge is contouring of organs, where the actual organ is located. So there are huge development in this field that the AI can actually help us to contour where is the organ, and then we can automate the organ dose calculation. We don't need to. There was also a question about the water equivalence, and this is also true. Actually, the phantoms are made of plastic or PMMA, but it's completely true that if we have a different organ, like the material is different, the density is different, the dose it will also impact on the dose. But when we can use the CT image directly and the AI to contour the image, the organs, then we actually already have a lot of more information. We can improve the accuracy.
Yeah. Now let me complicate a little bit this more for both of you, because and try to include here the image quality. What is the impact? And because there's a lot of radiographers attending, and I hope we can pass the message. What is the impact of the patient centering both in dose and image quality, if we don't keep the patient in the ISO center, which is in some cases a huge percentage, due to the fact that the tables of the CT scanners, they have this standard point where they stop, and then in some institutions that we have seen, they assume that position as correct, and they don't take into account the size of the patient. So what is the impact on this one in dose, and for Christoph in image quality, if any?
Definitely, if I may start, definitely there is a larger impact of that. It has never been really quantified, as far as I know, in terms of image quality, because we don't have yet the measurement facilities to do measurements of image quality objectively in CT. But what we know is from studies that a large from subjective image quality assessment, that a large portion of the images read to be non-acceptable is due to the fact that the patient was not positioned correctly in the center of the beam. So there is obviously a large amount or a large effect, and that depends also on what region you want to evaluate, right? And there is a dose effect, but maybe Paula want to answer that one.
Yes, this is a good question. Definitely, that is the challenge, is that this is really the system is defined in a way that the rotation is around the ISO center. So, for example, we have the bow tie filter, which is impacting the dose distribution when the patient is not positioned correctly, and we are also using this using the automatic the tube current modulation based on the image made in this wrong position. This will definitely have an impact on the dose.
Okay, let's go now to the dose, because we are talking about dose, organ dose, and we have a question, several questions about organ dose regarding the role of AI in calculation of organ dose, and Paula touched that a little bit. We have a question that in the phantom there is water, so how can you compare the dose of organ, because of organ composition is different from the phantom in terms of density? So how do we compare from phantom to patients? This is, I presume, what the question is. And my question to add, my question to add is, do we really need patient dose, or would you define specific scenarios where would you as medical physicists would recommend patient dose? Oh, sorry.
So first of all,
sorry, organ dose. I expressed.
Yeah. So first of all, the phantom what we use for dosimetry is actually made of plastic from PMMA, and this is absolutely. Who asked the question is absolutely right. The organ composition impacts on the dose, and this can be taken into account only if we have used a correct patient model where this information is included, and then we can do Monte Carlo simulation and take into account the organ composition. But if we just consider that it's water, yes, this will also increase the uncertainty in the calculation.
But if I may, for the organ dose calculations that you typically do, you would do that with either Monte Carlo simulations or with AI-based methods today. And in both cases, you would then try to make like conversion factors or calculate on a single patient basis the transformation or the dose to a single organ, right? And this takes in the conversion factors, or also this takes this water measurement basically as a calibration, right? This, or as a basis value, let's say it that way, not calibration as a basis value.
Any recommendation when to do that? In all patients, in some patients, when? Recommendations?
This is a big question, but first of all, I would like to say that, if we do Monte Carlo simulations, we would normally not use even the phantom measurements as a starting point, but we would actually use the measurements free in air and then the beam properties in the simulation. So because the phantom measurements are already a step toward organ doses. So in a way, when I do a Monte Carlo simulation, I actually have to take a step back to actually have all the like a basic data to do the simulation correctly. But the question, when we actually need this kind of detailed analysis of organ dose, I think this is really a relevant question. So sometimes we just develop methods because we can and we have the tools available, but we should really think that when we need this accuracy, when we really need this patient-specific dosimetry, and that's why I was also asking the same question in my presentation, that if somebody wants, so I had this example of a pregnant woman or another, but it's really an important question, I think.
Well, I think for the optimization, we would need it as well, right? Because as you said, there is now dependencies on what kind of radiation quality, for example, you use, what patient sizes you have. And there you do not want to just rely on a CTDI. There you need to have
This I agree.
organ doses, because you also might have some specific organs that are more affected than others for a single patient because of diseases or something like that. So in that case, we really need to know it.
Yeah, this you're right, but I would just like to make a difference between individual of one patient and then actually doing the optimization in a proper way so that we have the measurable quantity and then we do the conversion to that specific situation. So then we can actually, we can, for example, use a very good patient model, and we can use all the beam parameters and do the conversion to organ dose, but it's not an individual. So we don't need a CT image of that individual. So I think in most cases, in i-Violin project, for example, where we want to do optimization, it's enough when we can do this kind of measurable quantity and appropriate conversion. So we don't need the individual there.
Great. We have an interesting question from Hilde, which is here with us, and it's especially to do with how should we be dealing with tube current modulation.
Can you?
This is also a challenge. Sorry.
Okay, go ahead. Go ahead, Paula.
Yeah. So I think to be able to take this into account when we do dose calculations, we need that information. So because we can have this tube current modulation in angular direction and in the longitudinal, this jet direction, the biggest challenge is that we need to have that data out of the system in a format. So it's not only in the image, but in a format that we can use easily for example, for the simulation. And then, of course, if we have the tools, the simulation tools, where we can actually take this into account in the simulation. So this is not always possible. So in many programs, what we have currently commercially available or freely available, you cannot really have as an input parameter all information about the tube current models. And so it's an excellent question. It's really challenging. So there are two things: to get the data out of the city system and how to implement it in the calculation.
Great. We have another question that has to do with CTDI measurements. Is that if it's can we measure CTDI in more than one gantry rotation?
So this is normally we have done it in this one rotation, but as I showed this image where we have this phantom hanging in the air. So we are using this all the time in Finland, that we actually do the measurement for the whole protocol at once. So I think this is a nice way to do it.
Great, thank you. Let's go, Christoph. You talk a lot about image quality, and obviously without touching you about also image perception when you introduce the observer. How can we guarantee that the observer is okay? So so shouldn't we be doing image eye analysis or a gray level capacity discrimination amongst people that have to check these images?
Yes, definitely a very good idea. You have basically two ways. If you do a study where you use the observers for doing observer studies, then you need to check them in a certain way. You can do that either by having them read the stuff first and then look when you have large intra-observer variabilities, then you should maybe have another check. If you look for the readers in a hospital that read clinical studies or clinical cases, then you should first of all look for that they are adapted to the lighting conditions well, and that they are not too heavily tired and things like that. But the question is, how can you do that practically, right? This is not very easy. So I think that especially the tools that I presented at the end could be of large help, right? If you get an answer that a system, that an image you get is pretty good, it's on the upper level of image quality, at least absolutely acceptable for diagnosis, and you feel, oh, well, I'm not seeing a lot, then you might also have an indicator that you need a break. So this is something that's very practical that you could do with this stuff, right? You can make use of that to get your to get a quality control for yourself.
For both of you, honestly speaking, looking into the future,
Absolutely.
Do you see that AI will take over image quality analysis and those analysis like 100%?
No, not 100%, but it will make a strong task because you can do with AI some aspects that we can, or that where it is much more complicated to do it today for image quality assessment, like looking for image quality in different areas of an image and stuff like that. But there will still be aspects where you need the human observer. There will be aspects where you want to understand the physics behind. Sorry to name the physics, but I don't think that it will take over everything. It will make things easier in some points in image quality assessment. And
Paula, your opinion?
I agree with Christoph. So, of course, especially when image is involved, so there's so much data that I really see that AI can be a huge support. But AI will not do those measurements. And if we have this physical components in the system, so if we cannot, we always need a measurement, because otherwise we cannot see how the system is operating. But definitely it will help us.
Two conservative answers. I'm a little bit more optimistic that, to be honest, my vision is that in the next decade, AI will take over most of the things we do in our daily life. So we should be rethinking of what we should be doing. Now, again, just to go back to the image quality, because and Christoph, in one of your slides, you had all the technical specifications that impact dramatically in image quality. And what we have seen is that there is a huge heterogeneity, even in the same department, on how they use KV, MAS, dose modulation, whatever tool, and which has an enormous impact in image quality, basically including, for example, adapting KV or not when you use contrast. We haven't spoken about contrast, but that has a huge impact also in image quality. What, in your opinion, so what message can we give to the people that are attending on how to carefully use each one of these particular element of the exam, that each one of them alone interferes with image quality, interferes with patient dose, with organ dose? What would be the message, Christoph and Paula?
Well, if I may start again, Paula, I think you always need to have a clear idea why you would use what. And then we are developing in i-Violin optimization tools and assessment tools, right? So you can assess those, you can assess image quality, and then you can see what kind of output you get in terms of image quality and in terms of dose for the different parameters that you are using on typical or on specific patient groups. Let's take it that way. Or we are also, not our group, but the group of Hilde is developing optimization schemes where predicted image quality, depending on parameters for different, for example, patient sizes, KV, and so on, is predicted based on such model observers. So that can be used for your optimization to turn into the right direction. I think that's the message. I mean, there should be really an interdisciplinary team to look at that, seeing what is possible and what is maybe what could be advantages for a certain patient, let's say a patient size, a patient indication, whatever. And then you should try to verify first on these optimization tools. And then you need to verify at the end whether your system really, or whether your approach really paid off in the way that you wanted it to be by doing the assessment.
Thank you, Paula.
Yeah, again, I don't say that the AI is not, I really say that it will be a huge help with dosimetry also, but I just want to repeat that there is always a measurement behind. So I'm just thinking this black box. So when I will get the CT image, I don't want to go in the CT in the black box without knowing that there is some measurement, real measurements behind. So of course, AI can predict the dose based on many things, but what if the system is just breaking down and we don't get this information if we don't do any measurements or any physical measurements for the system? So I still think that we need some measurements also in the future.
Great.
I'm not sure if I answered your question.
Okay, we come to an end of this webinar. It's when everybody says, "Oh, why it stopped?" On behalf of Work Package 7 of i-Violin project, I really thank you for your outstanding presentations. It was a really very useful webinar I'm sure for everybody that attended from all around the world. So on behalf of i-Violin, thank you so much. And I will invite you, everybody, to our next webinar, which is in April 9, where we will go into the dose management. And for those that answered these recording would be made available on the a-Beer YouTube channel, that obviously all of you will receive the link for future. Thank you so much.
Graziano, there are two hands, so maybe these people want to write their questions.
No, but it was on the chat. Sorry. Yeah. It's we have to finish, unfortunately. Thank you so much. And as I was saying, you will receive the link to revisit this presentation if you want on the i-Beer YouTube channel. Have a good evening, good dinner for those that have dinner, good lunch for those that will have lunch, and a good sleep for those that are going immediately to bed after this presentation. Thank you so much. See you next time.
Bye-bye.